Hello everyone. In this lecture what we are going to see is about the transforms in general and mainly Laplace and Laplace-Steele transform and the generating functions, right, which is what is going to be used extensively in our analysis that we are going to see. In queuing theory, when we analyze a particular queuing system, it is often the case, except for the simplest of models, it is often the case that you are not able to obtain explicitly or even not able to do some sort of analysis to take it a little bit forward to get some insights in an explicit form, right, or in the usual domain. So, what is done in such situation is that then you transform the domain from one to the other and look at in the transformed domain, probably like your analysis could be done in an easier way, and that is what is being done generally, and the tools that helps us to do all these transforms in general. I mean, people who are familiar with dealing with differential equations, like how much is these Laplace transforms are useful, and probably the other ones are Fourier transforms, and its uses in different areas is also known. But in applied probability and stochastic models, also this transforms play a critical role in the analysis. So, in this lecture what we will try to do is that we will just try to recap and try to understand what is this and certain properties of it, so that it can be readily referred to later whenever we are doing the analysis with respect to a particular queuing systems, right. So, as we said that it is basically in the time domain, right, normally when we work on, right, is what our analysis is. So, any quantity, for example, whether it is number in the system at time t or in the waiting time of a customer, how long is wait, these are all in time domain, which has to be transformed to some other domain. Okay. So, a useful transform, which is transform here means that it is mapping from one space to the other, like typically these are all from mapped from some real space to a complex space. Okay. And this plays a queuing analysis, like it has lots of importance into this case. Okay. Now, let us see what is a Laplace transform. Let us define. So, let f be a function from this positive or non-negative real line to the real line, be a suitable function. By a suitable function I mean the function is of piecewise continuous and of exponential order, means it is at least piecewise continuous in any finite domain in this interval, and it does not grow beyond an exponential function, but it does not grow faster than a function of exponential function. That is what it would mean in general, but anyway technical part you can always look it up. So, for such a function the Laplace transform of f is defined. So, this is the notation that typically it might be given L of f of t or f bar. The bar is what we denote by the Laplace transform of s is defined to be this integral, okay, where s is a complex number, complex variable, and basically like the conditions are required where we have to take a suitable function such that this integral exists, that is all. Under broad condition it can be shown that this particular function is analytic in the half plane, this for some constant alpha, that alpha is related to this exponential order. And there is a one-to-one correspondence between the function and its Laplace transform. That is why you would see volumes of books, I mean a book which contains exclusively functions and their Laplace transform given as in the table form, right, because for ready reference, because for different function you obtain, and working with this would be in some sense equivalent to working with its transforms. That is what we will also be doing it. Okay. And there is one-to-one correspondence between the function and its Laplace transform, which means that if you know the function, you know the Laplace Laplace transform, or if you know the Laplace transform, then you know what is the function. So, some common pairs of functions and its Laplace transform, which again for ready reference, for anything it comes, you can just put it into this and then obtain this integral. But suppose if the function is the constant function 1, then you put this instead of the f of t, you put 1, right, then what you will end up with this, right, 1 by s. And if the function is t, so then it is t e to the power minus s t. So, if you evaluate that, you will end up with 1 by s square as the Laplace transform. In general, for t to the power n factorial by s to the power n plus 1 for, so these two cases are subsumed within this generic one, right, is what is the Laplace transform. Now, if I have e to the power minus a t, means f of t is also e to the power minus a t. So, you just substitute, then what you would get is this quantity e to the power minus a t and t n, meaning this one is, we know this, and this one is this quantity. Now, together the product, what would be this? It would be of this form. Okay. We can substitute and see. Now, cos b t is s by s square plus b square, sin b t is b by s square plus b square. Now, again e to the power minus a t and say sin b t or cos b t or anything you can combine, right, you do this, you will obtain this one. So, these are some common pairs, or any other thing that you normally encounter, you can always substitute here and try to understand, right. So, most of the things like we will be concerned with something of this kind of forms, we will be arriving at you will see like in the analysis when you go further. Okay. So, an example, for example, if I take this particular function, what is this function means? It is the probability density function of an exponential random variable, and if I can compute this, so this will be lambda by s plus lambda, right. Now, there are certain properties that you need to know so that you can use it, right. So, it is linearity property, right. The Laplace transform of a1 f1 plus a2 f2, where f1 f2 are functions, a1 a2 are constants, is given by a1 times the Laplace transform of f1 plus a2 times f2 Laplace transform of f2. So, it is a linearity property, right. This is again something similar we have seen in the example, but this is a generic property. Like if I have a function f of t for which the Laplace transform is f bar of s, then if I have this e to the power minus a t, then this will be this. Similarly, f of a t is 1 by a times f bar of s by a, and this is the derivative. So, the nth order derivative of a function, and if I want its Laplace transform, it is given by this expression, where this is s to the power n, the Laplace transform s, and minus this is sum where s I n minus 1 onwards all the way up to s is 0, which means in that case it is 0th order derivative, which is the function itself. Okay. So, and the function evaluated at 0 is what the Laplace transform of the derivative, and again integral, Laplace transform of such an integral, you can see that it is going to be this f bar of s by s. This again you can obtain from definition, but for any reference this is easier. Now, this is the Laplace transform of this kind of function is what is called the convolution of g and f, right. So, this is convolution function. This convolution function of g and f is given by the Laplace transform of such a convolution function is given by the product of the Laplace transform. It is a very important property which has lots of application that we will be using it in our analysis. And again limit property, right. If you want to look at this quantity, which is what will happen to the function as t tends to infinity, right, which will be same as the one you are looking at the function s times f bar of s as s tends to 0. So, this is, and the other side t tends to 0 of f of t is given by s tends to infinity of this quantity. So, even if you are in time domain, even if you are in the Laplacian domain, if you want, you do not have the function explicit form and you want to look at this kind of behavior, and this kind of results are useful, right. Like this, say looking at this is same as looking at this. So, these are certain properties of the Laplace transform which we might be using it. Okay. Differentials, integrals, convolutions and linearity and shifts and so on. Okay. A related transform is what is called a Laplace-Steele transform, which is defined for a function again under non-negative, defined on the non-negative real numbers as this, right. L star of f of t is f star of s is what the notation that we will be using it for Laplace-Steele transform, which is defined to be this integral. So, this integral as you see is the Steele integral, right, Riemann-Steele integral, whereas the first one is Riemann integral. So, this one is what we said that in probability review also, like we pointed out this kind of integrals will come. So, no matter, you do not need to worry too much on this, what is this, even if you do not know, but it's you will know soon anyway, the alternative ways of looking at that, okay, where the integral is the Lebesgue-Steele integral, okay. So, this one, right, this is what is defined as Laplace-Steele transform, as you might have known from this the properties of this subsumes both the discrete and continuous nature of this function f, okay. Now, in our case, what is our f? Of course, it also requires some condition on this particular function f. Of course, this function is we have given it. So, now you need to impose some condition on this f, so that this integral is well defined. For us, there is not much problem on that count, because we consider this f to be the distribution function or cumulative distribution function of a non-negative random variable x. So, f star of s is simply this particular expectation. You see, like whenever you encounter this, whether it is discrete or continuous or mixed or any random variable, for us in our case, like the Laplace-Steele transform, you can always relate to this particular expectation. And the expectation you know how to compute. So, this is nothing but this expectation of e to the power minus s times x is what the Laplace-Steele transform, and which is what is this quantity is, okay. And again we consider our f in Laplace transform, whenever we are defining our f would be there the PDF of it, okay. Now, suppose for an exponential random variable with mean 1 by lambda, you can obtain the Laplace-Steele transform to be this, which you notice that is the same as the one that you have obtained as a Laplace transform of its density function, okay. Now, for a discrete random variable x, right, which where x takes value 3 with probability 3 by 10 and 4 1 by 5 and 9 it takes half, you can see that this Laplace-Steele transform is nothing but this quantity. Again recall that this is nothing but this expectation, okay. Even if you do not know the theory of Steele integral business, so you can always use this to arrive at that. So, that is what it is, okay, and that is what is the Laplace-Steele transform, which we will call it as LST. For later on we will simply use the abbreviation LST for this purpose. So, this is nothing but 3 by 10 times e to the power minus 3s and 1 by 5 times 4 e to the power minus 4s and 1 by 2 times e to the power minus 9s, and you sum all these things is what will be your Laplace transform or Laplace-Steele transform of this, okay. So, when a non-negative random variable x has a PDF, then as we just noticed in the case of exponential distribution, the Laplace-Steele transform of the distribution function, which is what this is, equals the Laplace transform of its PDF, the probability density function, which means when you have a non-negative random variable which has a PDF, it's continuous random variable, it's a continuous type random variable. When it has a PDF, then whether you are talking about Laplace transform of its PDF or the Laplace-Steele transform of its CDF, they mean one and the same, okay. More generally, one can say that if I want, like this is, you see, small f bar of s, not capital F bar of s, we are not inferring that part. So, more generally one can show that this is what is the case in that scenario. F star of s is equal to s times f bar of s, as you see here, which is what for any such thing that you can find. But this is nothing but the equal to the Laplace transform of its PDF, right. That is what. So, this also like you can keep it in mind, sometime this will be useful. Okay. But for a discrete, right, you do not have this Laplace transform function, right. So, that is the reason why you always deal with Laplace Steele transform, so that you are incorporating both the quantities at in one transform or in one tool that you want to use it. So, basically further it is a continuous like exponential or a discrete like this 3-point distribution, you will have this Laplace Steele transform. Okay. Now, for example, if I pick this function, okay, if this is what is given to be the function, remember look at little carefully this is not of a continuous type, not of a discrete type, but it is of mixed type, meaning it has a mass of 1 minus rho at the point 0, and for t strictly greater than 0, this function is continuous and differentiable. So, for t strictly greater than 0, it has a PDF, and at t is equal to 0, there is a mass, and right. So, the mass is 1 minus rho. So, the remaining mass of 1 rho is what is distributed between t strictly greater than 0 and infinity, right. So, it is a mixed type random variable, right. Now, if I use the definition of its Laplace transform of f, right. So, what you will end up is, again you remember that it is expectation of e to the power minus s times x, and this is what is Laplace transform, which is nothing but the point mass at 0 plus rho times the d e to the power minus st and d f of t, right. D f of t in that case for t strictly greater than 0, it is differentiable. The derivative will be mu times 1 minus rho times e to the power minus mu, this quantity is what you get. So, this is what it is. Now, you can evaluate this, and you simplify, finally you arrive at this expression, directly computing the Laplace transform. Now, you can also obtain the above using this relationship, like you have this f bar of s, you have its you can try to obtain this and so on, and then you can see this is an exercise that you can try. Now, the properties of LST is similar to the properties of Laplace transform, again like f of t and f star of s both have one-to-one correspondence with each other, which means this can be uniquely determined from this. So, if I know this, it is equivalent to knowing this. Okay. Now, certain properties, again this is one property that there is one-to-one correspondence, but the most the other useful property in our analysis turns out to be that this part, the LST of the convolution of independent random variables is the product of the LSTs of individual random variables, right. That is, suppose if f star of s is the Laplace Steele transform of x and g star of s is the Laplace Steele transform of y, then the Laplace Steele transform of x plus y, if x and y are independent, is given by the product, right. And you know that this is what that means, that the convolution component is what the property, that is what we are stating it here. Okay. The other useful property is this continuity, that is, if xn is a sequence of random variables with distribution functions and corresponding Laplace transforms, and if as n tends to infinity, if fn tends to a distribution function f that has a LST of this, then the corresponding the transforms will also tends to the corresponding transforms, and also conversely. Okay. So, this is sometimes useful in finding out the limiting form of certain distributions that you might encounter. Okay. Now, we can relate by looking at this Laplace Steele transform, that you just notice that it is expectation of e to the power minus sx, right. And recall, if you have a non-negative random variable as we have it in our queuing analysis, that the moment generating function mxt is nothing but e to the power t x, which is given by this, if exists, right. We need to worry about that part. So, this is similar to the Laplace Steele transform of f with minus s replacing t. That means, if my mxt is nothing but f star of minus t, right. Whatever properties that I have for Laplace TJ transform, I can transform now to this moment generating function whenever this exists, right. So, this is the connection. And for example, for an exponential random variable, we know that this is the moment generating function and this is the Laplace TJ transform, and which is the same as Laplace transform of its PDF, right. Or for the random variable, we can refer to that. Now, recall for a non-negative, we also know this function, which is nothing but the characteristic function, which is defined to be this. Again, in this particular case, we can relate this to LST with minus s replacing this IT. So, this is the relationship that you might find, right. So, for an exponential, for an example, this is what is your characteristic function, but this is what is the Laplace TJ transform, that you can see. And from here like I can get the moments of this, right, that is what is important. So, this expectation of x to the power n, the nth raw moment for a random variable, if I have the characteristic function in my hand, what I can do, I can find its nth derivative and I can substitute it at derivative and evaluate it at the point 0 to get this quantity and multiplied by this I to the power minus n to get this. Or this quantity, if I have the MGF in hand, then I can use this expression, that I can find the nth derivative of this and then I can substitute it, evaluate it at 0. If I have the Laplace TJ transform, then I can find its nth derivative of this Laplace TJ transform, evaluate it at 0, multiply by minus 1 to the power n to get this moment. So, why this is relevant? Because if you know, we have said that the transform and its the function has a one-to-one relationship. So, what normally instead of working in time domain, we transform to the transform domain and work on that and then simplify it. Finally, you find the inverse Laplace transform or inverse Laplace TJ transform to get back to the time domain. Now, many times that cannot be possible, like it will be very complex in nature. So, in that case what you do is also at least try to obtain moments of the random variable originally. So, you can use this kind of expression directly to get the moments. You do not even need to invert back if that is what is a complex in nature, right. So, that is a beauty, that is an advantage that you deal with such quantities in a different domain. But we will be content with MGFs and Laplace transform or Laplace TJ transform of mainly continuous random variables, meaning that of course, whenever LST means if we are dealing with discrete, of course, this will be Laplace TJ transform. Continuous means one can refer to any one of these in a way, but what we meant to say is that we will deal with the MGFs mainly rather than the characteristic function. So, we will be content with this. So, because of this relationship, MGF too have similar properties as you know. So, there is a one-to-one correspond between MGFs and its probability distributions. The MGF of sum of independent random variables is the product of MGFs of individual random variables, that also you know. So, again these are all one and the same. So, it is have these similar properties that you have here, right. The other quantity that is of interest to us in our queuing analysis is what we generally call generating function. We just said that moment generating function because it is the moments are used to construct such a function, right. So, and it generates moments like we just saw this here, right. So, expectation of n can be obtained from its moment generating function, right, the same thing. So, the other one is what we call probability generating function, which is an example of a generating function of a sequence and equivalent to the Z transform of the probability mass function, and these generating functions are in general useful in solving difference equations. Difference equations not just arise in our queuing theory, but elsewhere in many different fields of applied mathematics you will encounter difference equations. And while to solve that, the Z transform is what is quite helpful in using that, and we will also come to know soon. So, this is probability generating function. In our language, in probability theory, this Z transform equivalent in a certain form is what we call it as probability generating function, which is defined for a random variable, a discrete random variable with this PMF where the support is 0, 1, 2, 3 and so on, it means non-negative integers. Then this one P of Z, sometimes some books call it P of S, does not matter, is expectation of z to the power x. Again you relate, this is nothing but an expectation, that is expectation of z to the power x, which is nothing but this quantity, is what we call it as the probability generating function. So, what you do here is that you take each of these pn's and you put a tag, that is z to the power n, and put together and put it in a single basket, rather than representing all p1, p0, p1, p2 and so on. You represent it in this form, and as a coefficient of z to the power n, you can always extract pn. I mean, these are all used in that manner, right. You represent it in a single form. So, this is whether I represent in this form by giving all p0, p1, p2, p3 and so on, or I just describe this function p of z, it is one and the same, right. So, and this is what is called the probability generating function, because the coefficients generates the probabilities of the discrete random variable which has support on non-negative integers. And this is similar to MGF with now again you see e to the power t z, if you replace by e to the power t, then what you are going to get is the for such random variables, if you have the MGF, then you can find the PGF using this relationship, or if you have PGF, the MGF is given by in this case. So, for example, for a Poisson random variable, we know that this is the MGF. Okay. Now, this e to the power t, if I replace by z, this is going to be the probability generating function, right. So, you can try to expand this here, right. E to the power minus lambda will be outside, and then there is e to the power lambda z, you make it as a power series expansion and you extract the coefficient of z to the power n, you get the probabilities. So, whether I describe the probability distribution through the description of these pn's or by giving this function, then you should know like what is the transform. So, we have given, I mean in the tables of the distribution and its MGF. So, MGF, if you have, like if you replace e to the power t in the MGF by z, what you are going to get is the corresponding transforms for appropriate random variables like Poisson and so on, geometric, Poisson. These are the typical random variables that we will encounter. So, if it is just sufficient that if you know this few of these transforms. Now, again this p of 1, as you know, like I mean in simple terms, suppose if I think like suppose if I put z equal to 1 here, what will happen? This is simply sum of p of n, which is must be equal to 1, right. So, that is what essentially we are saying in the limit for this function, because we need to worry about the range for which this is, if it is little bit more than that, then the properties of power series comes into play when you are differentiating and passing the limit inside. Okay. So, the series converges absolutely for at least for all complex numbers in this domain, but if it is slightly more than 1, then we will not have a problem, directly we can substitute, otherwise we have to take the limit is from below. This is a technical part, we do not need to worry, but for our cases we are in good shape, you do not need to worry on that. So, you can simply substitute 1 and then see that this is equal to p of 1 is equal to 1, that is the property that you need to remember. Then again, if I differentiate this, for example, simply you can think, if I differentiate this with respect to z, then I will have n times z to the power n minus 1. So, I will have a form of some n p n z to the power n minus 1, right. Now, if I substitute z equal to 1, then what I am going to end up with? This quantity p dash of 1, differentiate and substitute 1, then what I am going to get is expectation of x, right. Similarly, if I do this double derivative and substitute 1 and then do this, then I am going to get expectation of x square. So, the double derivative or the triple derivative or in general nth derivative evaluated is 1 will give you this moment, which is what is called the factorial moment. This is nth factorial moment, right, x into x minus 1 into x minus 2 and so on. If you take the expectation of that, that is what is called as the factorial moment. So, that is what you will get from this. Remember, MGF you differentiate and put 0, you will directly get the nth raw moment, but here you differentiate with and put the value 1 or evaluate the derivative at the value 1, then you will get the factorial moments from the probability generating functions. Okay. Now, that is a simple exercise or example that you can see. So, you have a scenario where xn are independent and identically distributed discrete random variables with its probability mass function described by this probabilities Pk with the corresponding probability generating function P of Z. Okay. Generically we are taking it. Further, suppose that this capital N is also a discrete random variable with probability of n equals to n as Gn and with its PGF being G of Z, which is given by this expression. Now, assume that these random variable xn and n, these xn's already they are independent among themselves. Now, they are also independent of this n, that is what n is independent of xn. Now, you define this quantity S suffix capital N, which is nothing but x1 plus x2 plus up to x suffix capital N, where n is already a random quantity, and let this quantities PGF be H of Z. Okay. Now, it is an exercise for you to show that this quantity is given by this H of Z is equals G of P of Z, right. That is what you can show. Easy, you have to use the conditional argument, you have to, and that practice should come, that practice is, so this is one start. So, basically H of Z, you know what is H of Z, right, it is basically this quantity essence distribution, and if you want to call that as some Hn, then using that you can do that. Say for example, you can define Hn is basically probability of Sn for fixed n, okay, equal to some okay, this n and that n are different. So, I have to make it or Hk, I will call it, is equal to some k is what, then if the distribution of this, now this particular n is also random in our case, right. Then you condition on that, and then you will use this expression, and then you will arrive at finally this one. You can easily do it, it is not a big problem. Okay. Now, but what is important for us is that from this, using the properties that we have just stated, you can deduce that the expected value of this is nothing but this quantity. Okay. If it is some fixed one, if S is a fixed one, they are all IID. So, S1, suppose S10, suppose if you are looking at it, then there are 10 such random variables. So, expectation of this S10 is 10 times expectation of S1, that means that fixed value instead of this times expectation of Xn is what, then you will know. What this says, when this is random, then this particular quantity is to be replaced by this expected value of this particular random variable Xn, which you can deduce from here. Similarly, variance of Sn is given by this expression, also you can deduce, right. So, these are all some simple exercise that helps to get you started. So, you can try it in these examples. Now, for practice again, you can consider the above, means this whole thing, you keep this as generic Pk, but you assume this n to be that not just any generic random variables, but this is a Poisson random variable with parameter lambda, and see like what would be this. Now, what is that means that the form of G the form of G which is the Poisson random variable, what is its probability generating function. So, this will be then the G form but P form you still retain is P of Z. So, that is what is the form that you will. So, you know what you will obtain in this case. Okay. You will obtain that as a compound Poisson distribution. Again, you can extend the above by considering this xn's as the continuous random variables, right, rather than discrete here, with it has a PDF f and Laplace transform f bar, and you can deduce that the Laplace transform of this quantity is nothing but this quantity G of f bar of s is what then you would obtain here. This again, now you can extend a similar exercise where now it is continuous. Now, where does this kind of things do occur, and where do we worry about these kind of things? So, let us look at like this typical simple example that we are giving here. So, this suppose there is a clinic and the patients are visiting the doctor in the clinic. the number of patients visiting a doctor is a Poisson random variable with mean lambda, and the time taken by the doctor on a patient is IID uniform in 0 to h, where say in minutes. So, he will take the time to treat one particular, or the time up to which the doctor spends on a particular patient is uniformly distributed between 0 and 10 h. So, suppose if you assume to be some 5 minutes or 10 minutes. So, it is between anywhere between 0 and 5 is what he is going to spend on each of this patient. Okay. Patients arrive at a Poisson random variable with Poisson process. Okay. So, number of patients visiting the doctor is a Poisson random variable is what then we are assuming here. Now, if you want to find the mean and the variance of the time taken by the doctor to complete the consultation of all the patients, right. So, what you have here is the number of patients, you can relate it to this n, okay. This xn's are the time taken to serve a particular patient. So, this is given to be uniform and 0 h, this is given to be in Poisson random variable. So, you can simply use this relationship to get the transform of this, and from there you can obtain mean and variance. So, you are interested in say what is the time taken, mean time taken by the doctor to complete all the patients, to attend to all patients, and what is the variance of that. Suppose if you see, since you do not know how many patients would have arrived during a particular time interval in which your consideration, say for example in a day, okay, it is random according to some distribution, and the time taken is also not deterministic, it is also random according to some distributions, right. You are assuming that they are to be independent because there is no relationship between the time taken for a previous patient to the time taken for the next patient. So, that is you are taking to be IID for ease, and then some distribution in. Okay. Then you want to see like what is the overall mean, variance, mean. So, suppose this is a simple clinic with a single doctor, it is fine, but if it is a big clinic where there are multiple number of doctors, then to understand like how many doctors are needed, or how to increase the capacity, or whether over capacity, overstaffing is there, everything to analyze you need to understand, but things are random here, right. To understand all those things, because your interest if it is only mean and variance. So, now remember, if I want to compute the distribution of this, it will be very complex, but the mean one I can obtain it here. If I know the mean of mean and variance of the n and xn, I can get the mean and variance of this Sn. So, how do I arrive at this if I have to do this analysis, right. So, this is the expression that you would have. Again, in queuing situation you would find many a time this kind of scenarios, right. Given a time interval, how many people would arrive, how much time a server would have spent in it's similar situation, right. So, this is something similar to that is what then. So, such kind of situations would arise, it is not just in queuing and elsewhere in other stochastic models as well, right. For example, biology or DC, I mean all these kind of things, like you would find these are so common. It is not just in queuing, but it is also in more general stochastic process, this kind of things would come. So, to understand that you will need this, but the tools that you use, you see here the PGF, if I have, I can answer or I can handle this kind of scenarios with this kind of knowledge. Okay. So, these are all the techniques that we would need from the transform thing, Laplace transform, Laplace TJ transform, and the probability generating function. We will use mainly LST because it is same as LT, and it can incorporate discrete random variables as well, and PGF whenever it is much easier than the other one to handle in such scenarios, because you are dealing directly with the probabilities, you are working with probabilities, and then inversion you will give you probabilities as well, right. So, that is what it is. Okay. Okay, so these are all the tools that we might need. You can get familiarized with this, and then we may get going in the next lecture. Thank you.